We are very happy to have Oded Margalit here. Last time we had him in the colloquium was maybe 14 years ago. Back then he was still at the IBM as the riddle master. He still likes riddles. Nowadays he's with Next Silicon. Maybe you tell us a bit about this hardware company, and it's also affiliated with Ben-Gurion University.
Hi, thank you for the introduction. Nice to see so many familiar faces. This talk doesn't usually people forget it necessarily, because if they don't put it, then they actually claim that their employer doesn't have this claim, which is a claim in itself. And of course, it doesn't represent my past, current, and future employers. I'll say some things that might be offensive, so tell me if it offends you. I'll try to avoid it. And of course, how can we start without a riddle? What's the connection between this formula and my talk? So if you don't
bitwise n?
Bitwise n. So that's the parity of the prime. You multiply all single digits primes with the exponent of 2 for the even one and 1 for the others. There are 3 types of mathematicians: those who know how to count, those who don't. If you know how to count, then you can compute this 2 squared times 3 times 5 times 7, which is 420, the room of this talk. Okay. I came from, you probably chose the room just for that. The combinatorial seminar was held on room 210, which is even simpler, just multiplying all the primes. This is a Schreiber building. I saw it before it was built, and I was in the computer lab of the School of Mathematics, PDP 834. So it's a little nostalgia. But let's start with riddles. So what is a good riddle? I have 3 criteria to define a riddle as a good riddle. First, it's easy to describe, and of course, it's different people may claim that different statements are easy. You can have a very nice differential geometry riddle that requires you to read several books in order to understand what the riddle is. I have a nice riddle that I guess all of you will understand it, but some people may say that it's not easy to describe. And the question is, if can the function sinus can be have a d-normal output? So first explanation, floating point 64 is a way to IEEE 754 standards to represent floating point numbers, and it has the exponent, sign, and mantissa. There is an implicit one in the mantissa that saves the bits, but if you lose it, then you get to d-normal, a very, very small number. So for example, in ST32, numbers below 2 to minus 127 are d-normal. And someone in my work asked me, I'm writing the hardware implementation of the sinus on our accelerator. And it cost me a lot of silicon to compute the if the output is d-normal, then do something. Can you prove that you can't get the normal output? So sinus is a very simple function between -1 and 1. It can get a very small number if you get a very small input. The Taylor expansion near 0 is x, but some maybe 2 pi or 2 million pi plus epsilon is a normal floating point number, and the output is the normal. So I started thinking about it, and After a while, it sounded very familiar, and then I realized that a year earlier, in the IEEE Extreme competition, I used it as a challenge. Actually, what I did is, the IEEE Extreme is a programming competition. 10, 15,000 students around the world are participating each year. You are invited to join if you want. And you have 24 hours to solve several programming language challenges in any computer language you want. And how do you write a hard problem? How do you write a hard problem? You start from the end. You start from the trick that solves it. And I chose continuous fractions as a trick. And then look for a problem to as an envelope. And I did it. I asked, actually, it's a little harder with cosinus, but I'll leave it as an exercise to the reader. The only reason I put this is actually two reasons. One is to brag about how you can find in real life work things that you thought were useful only for riddles. I find it very entertaining. And second, just to explain the first criteria for a riddle, if you have to get a few paragraphs of explanation in order to understand this line, then it's not a riddle, it's a question, because it doesn't hold for the easy to describe. That's the first. The second is it's not only easy to describe, it's hard to solve. Otherwise, how much is 1 + 1 is easy to describe, and it's vaguely answers the third criteria, but it's not a riddle. It's just a waste of time. The third criteria is it has a simple solution. So simple solution, 1 + 1 hold. If you add the aha, the way that it's not only simple, but it gets you some kind of gratification feeling to find this simple solution, then you have to find a different example for the second criteria, not hold. A friend of mine, a Fermat theorem, for example, is a good riddle. If the proof on the margin of the Diophantus book was right, because it's easy to describe, a to the n plus b to the n equals c to the n, it's hard to solve. 350 years people try to solve it, but the problem is it fails the third criteria. The solution is 10,000 page long proof. It's not a riddle, it's a hard question. Okay, a friend of mine has a different definition of a riddle. He says that you start here and you want to get here. If you want to get here, that's 1 + 1. That's a simple solution. But if you have to somehow go backwards and then get to the solution, then this is a riddle. I like my definition, but for the sake of completeness, it's not the only definition. Okay. Here I'm starting to offend people, so I apologize. There are sociologists that psychologists like to laugh and say sociology is only applied psychology, and the same goes for biologists holding an octopus in his hand and says that psychology is just applied biology, so actually everything is biology, and the chemists say that biology is just applied chemistry, and the physics person says that which is just applied physics. It's nice to be on the top of the world and the top of the food chain, and way back the mathematician says, hey, I didn't see you there. So my first degree was in pure mathematics. I completely sympathize with this place. The way that the reason I said it might be offending is because there is the computer science and the computer engineers. And the computer engineers are there. They are building the bridge instead of doing the interesting part of proving it can be built or things like that. There are a lot of jokes I can maybe later. A game. That's a simple game. I use it usually when I travel in traffic jam and I see the license plate of the car in front of me. And we have something to write on. The board is probably behind. Here, this one. So give me a 7-digit number. No matter what.
1, 2, 3, 4, 5, 6.
Okay, it's not a random one. Yes, yes, random is yes, like the XKCD 4444. Yes. Okay, your task is to add plus, minus, times, division, and parentheses between those digits, and to get to 100. So, for example, one way to do that is
You're allowed to use also exponentiation?
no square root, sinus, nothing. Just the 4 basic operations, and you can't join digits together. So this is, you can't use it as 123. You have to split it, and
So they can order?
and in the same order. Okay, anyone has a solution? There are yes,
You do 4 times 5,
20.
yeah, and then you can do parentheses. No, not even parentheses. 2.
That's 1 times 5 times 4 times 5. That's great. Okay, so I wrote it as this is the traffic jam. I wrote it as a challenge a few years ago in the same programming competition. And what I did is I told them, this is the script that is going to check your solution. I'm going to give you a 7-digit number as input, and you should give me a 7-bit something as an output, and I'll test it like that. The first test is to see that after deleting all the signs that I allow you to add, the input is exactly the same as the output. If not, you fail. So you must use all the digits in the same order and use only plus, minus, times, etc. The second check is to see that there are no 2 consecutive digits. So no 2 consecutive digits can be found. You must use an operation between any 2 digits.
Why did you allow backslash?
It's not a backslash. Minus is a range. It's easier to write it at the beginning. A minus B, Z is all the letters between A to Z. So it's just an escape sequence. I should have wrote it first and then you omit the backslash.
Or use something other than system.
Yes, exactly. Yes. And then the last check is to run it through BC, the calculator, to make sure that you get 100 up to a rounding error, because in some cases you can divide and multiply, and if you do it in a finite precision, sometimes you don't get 1, but rather 0.9998. Okay, and then I asked solve this problem, and it's very easy to see that it's unsolvable. So how can you solve it? There are too many zeros. There are not enough options what to do with the remaining digits. You can enumerate all the possibilities and make sure that under the definition that I said, you can't solve it, but under the script that I wrote, you can solve it. Because
Star is exponentiation.
Yes, but
You're allowed to have star. Yeah.
I'm not sure if yes, you're allowed to have star. I'm not sure. I think caret is the exponentiation and star is an error. But and even if you have an exponentiation, you can't solve it. But you are in the right direction. The way to solve it is 5 times 5 times 4. All the zeros you can add, subtract. The problem is the 7 here that you can't get rid of. So you put a comment. slash star star slash. It's legal because it's division in the BC regarded as comment, so it's legal. It passes the. I'm very proud with this challenge, but here is how I looked at 2 a.m. In the competition, 2 a.m. 01 when my challenge was published, and the reason is you have to publish the challenge description, some test cases, for example, how to solve this one, this is a valid solution, this is not a valid solution, etc. And then a secret testings where you have to solve the problem. And I mistakenly put this one in the test case with the solution. So instead of letting them enjoy the challenge of debugging their program, finding why they can't solve this, etc., for hours, I just okay, that's a nice story. A different story, HVC, Hardware Verification Conference at IBM. They asked me to write something to challenge the participants, and I said, oh, send this program to them in advance, and the solution, the correct solver will get some award in the conference. What you see here is a very long program that looks like HVC. That's the name of the conference. And if you see here, there is the input buffer, the input, the buffer, and the memory, which states the acronym of IBM, slightly hidden in as a subtle PR. At the end, they didn't use it. I don't know why. They don't want to torture the participant. But if you want to solve it, you have the recording, you can try to solve it. The first question is, what is actually the question here? As you see here, find the shortest input that covers all feasible memory. So it has an input. This is a computation machine that accesses a memory. And in order to verify that the program writes, for example, the Intel floating point division bug was a bug that a table was not tested correctly, and there are 5 entries that could have been addressed, but they didn't check it, and it was 0, and then they paid $475 million to recover the bug. So we want to check all the places in the memory to see that it actually works, and you want to do it in the shortest input. So reverse engineer this program, understand what it does, and then you'll get a very nice combinatorial problem, and then solve it. The question about the shortest sequence, I'm not sure for this version. I think this one is close, but you can easily get an open questions with a slight variation of the numbers. So if you want to publish a paper about solving a combinatorical problem, etc., you can use this in your paper if you want to scale the readers. This is another. You can guess which company I worked at when I wrote it. This is a program, actually a program, and you have to write a simulator for this program. You write something that gets the same input and produce the same output as this one. Anyone recognize the programming language? It's written, yes. Brain, 4-letter words will start with an F, BF in short. For those of you who don't know the program, it's very simple. You have an infinite one-sided band of zeros, and you have a head pointing to the start of this sequence. And then every time you go, you get this greater than, you just move to the right, and less than you move to the left, you move the head. Plus and minus, you change the value increment or decrement. It's a byte, 8 bits. So if you increment 255, it goes back to 0. That's two other commands. Dot is just omit as an output the value that you are pointing to. So that's the output. Comma is input. Take the input, standard input, and put it at the place that you are pointing to. And up to here, that's only a single line program. It's very degenerate. You can't write a lot of things in that. But once you have this, you can have loops. What this one does is looks at a pointer. If it's 0, then goes to the matching close brackets. And the second one goes back to this one. So for example, what does this code do? Starts where you are pointing at. Decrement. Yes, that's 0 value. If you have a place in the memory, you want to zeroize it, this 3-letter program does it. If you look here, you can see a lot of interesting patterns. For example, this one. Left, 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 right, left. Why do I want to do that? Because my program was shorter than the logo, so I have to fill it. And this one is a dummy knock, just to fill it.
Unless you're at the beginning and then you...
You're not at the beginning, yes. And if you first do the right, then that's okay. And here you can have, this is zeroize, I called it, I showed you. This is another zeroize, but with a minus plus redundant, so we can remove it. If you remove it, it will shrink by 10–20%, but it's still an interesting challenge to find.
What is the exclamation mark at the very end?
Oh. All the knobs were, thank you for the question, were even, plus minus left, right. And my program was odd. And to fit into this, I have to put actually, if you look here, all other characters are not. All the spaces, the new lines are disregarded. So this one is disregarded as well. And this one here, that's the output loop. I'll write it here to show you. What does it do? Prints the bytes one after, actually from the ends to the beginning, one by one, and stops when it gets to 0. So it's null, print a null terminated string.
Closest to the Turing machine. With the using implicit.
Yeah, so it's a very popular language for exactly for the right kind of people, and I like it very much. This one, again, I was working at IBM, and they asked me, I think maybe I showed this one in my previous talk, and they asked me to write a challenge to recruit students from the Technion. It was a Yom Zrakor. And I said, what do you want them for? They said, hardware verification. I said, okay, this is a circuit that computes a function from 4 bits to 7. There is a bug in it, fix it. So first of all, you have to guess or otherwise find what the correct function should do, the function from 4 to 7. Can anyone guess what a function from 4 to 7? Exactly. The 7th segment. It gets a number between 0 and 9 and prints the 7 segments that should be lit to show display this number. As a clue, the arrows here pointing a very awkward permutation. I chose a 7-segment chip, put it in the simulation here, and this was exactly the right ordering of the wires to debug the function. There are 2 problems here. One is that I optimized it manually, and I forgot that 2 different gates are actually computing the same function, but the error actually was here. That's the gate should be XOR instead of.
So you put this also on ponder this, right?
Yes.
How many
Uh,
students solved it?
hmm?
How many solved it?
600 people tried to solve. And in the ponder this, several people solved it.
One succeeded.
From the Technion, I think only one or two, but several solved it from ponder this. One of them sent me this picture and he said, I built it 35 years ago and it wakes me up every morning since then. And the solution to your problem is this one. So that's a nice riddle. Another challenge that I used in IEEE Extreme is this is a assembly 8086 program, and your challenge is to write a program in any one of the 30 supported languages that actually do exactly the same. And the question to you is not try to reverse engineer it. I don't expect that in real time, but how can it be difficult? Because it's a very short program. The assembly of 8086, people ask me, so I refer them to Intel 3355 pages of the data sheet of the chip. It's very easy. And when they complain, I gave them an online simulator that can, disassembler that can get actually the assembly, that's a few lines. How can it be difficult to, you can just write a simulator in half an hour. So
The wrong friend said, you modify the instructions.
okay, that's a good idea, but no,
Fine.
it's first of all, in the simulator, you can, it's a little more complicated, but you can deal with that. And second, no, this was a very straightforward assembly program without any code modification.
Go-tos?
Go-tos into the middle of the instruction. No, I like it, but no, this one is not the case.
Really homomorphic encryption.
Close. How do you sort numbers? There are a lot of algorithms. One of them I like is the following. Generate a random permutation, test if it's sorted. If yes, you sorted it. If not, try again. The running time is n factorial times n, because you have to check, divided by 2, because on average you will get. So this one was a similar one. I won't spoil you all the details, but it implemented a very, very simple algorithm in a very awkward, unoptimized way. The competition is 24 hours, and if you could just run a simulation, it would take a year. So you have to understand what it does, and then write a few lines of code that does it as it should. For example, sorting using even bubble sort or something. So this is the function. This is okay. I can. This is actually the reverse engineering of the problem of the program, but I will skip it. Maybe we'll go to it later. Garden hose problem. Alice and Bob has n bits. Alice has A, Bob has B, and they have, this is the model. They have a wall that separates them, Alice on one side, Bob on the other, and they can't communicate other than the way that I'm going to describe. But before giving you the details of this nice combinatorial problem, I'll explain when did it came from. Well, it's a quantum, it's a place-dependent encryption. Let's say that you have a road and you want to communicate with someone only if it's in a specific place in the road and nowhere else. How can you do that? You put two receivers, transmitters in the two sides of the road and send him two photons that if he's in the exact same place he should be, they should arrive simultaneously to him, and then ask him to get these two photons, compute in 0 time a function of these two photons, and send the answer to the two receivers. If he is in the right place, he'll get them simultaneously and will answer the right question in time. If he's not, then one of them will get earlier, but he won't be able to transmit the answer until he gets the other one. and by the time delay, I know that he is not in the right place. There is a way to cheat this encryption by using entanglement, quantum physics, all kinds of nice things. And the combinatorial question is actually this model. If Alice and Bob want to cheat in this kind of way, they have to use a lot of garden hose. And now I'll explain the model. Alice or Bob can put this, don't know how you call it, mufa, the shortening of two pipes on his side, depending on his value, secret value A. And Alice does the same, depending on her secret value B. And she has another tap that she can connect to one of the hoses. And now, when they both did what they did, they open the tap and the water flows, and there is a puddle in one side of the wall. The side of the puddle is the output of the function. So if, for example, they want to compute the function A equals B, this is a solution for three holes and a single bit. Alice and Bob has a single bit. What Alice does, it connects the tap to the first or the last, if it's 0 or 1. What Bob does is connect the middle one to the first or to the last, if it's 0 or 1. If they have the same bit, A equals B, the water gets into the left side. If they have a different bit, so Alice did that and Bob did that, then you can see that the waters appear on the other side. So this is a solution for finding if A equals B in using three hoses. This is a solution finding for 2 bits if A equals B using 4 hoses. Again, if you take the left and the right side from the same place, it always the water always ends up in the left side. But if you take the left side, give me two bits. Left side 0 to 3. Random number?
0.
0. Okay. The right side?
1.
1. Okay. So it goes through here, and it ends in the right. So you can choose all, check all the 16 possibilities. This 4 hoses actually implements the solution for A equal B, for A and B are 2 bits numbers. What happens if we get 5 bit numbers? So apparently it's you can solve it using 8 hoses. But actually the question can be generalized, because Alice and Bob doesn't have to get a binary number. They can get an integer. So this example, this problem, for example, can be solved with 36 possibilities instead of 32 to the fix. So Alice and Bob gets a number between 1 and 36. I can draw you a picture of these 36 possibilities of connecting the sides, and
what if Alice has 0 and Bob has 3?
okay. 0 and 3.
Ah,
so
the other one.
the water goes through here, then goes through here, and then goes back to here.
I see.
And thank you. It's a good question. The second time. It doesn't have to spill immediately. They can travel as many as you want. So I asked it in front of this. I thought that 36 is the optimal solution. It looked nice, 6 squared, etc. But I wasn't sure, and I asked only to 32 for 2 reasons. One is to confuse the readers to think it's power of 2, and the second to make the riddle a little easier. And then I started getting 39, 30, 42, etc. And I was actually very I liked the fact that they solved a problem that I couldn't, but then I tried to beat them, and it was actually a competition nobody in the world knew about. I was keep receiving solutions via email and sending them, okay, correct solution. And each time I got a solution, I ran my program again, trying to beat them and have a better solution. And I managed to do that for a few times. And then I got an email from someone who said, I have a solution for the 32 you asked, that's simple, but I also have a solution for 49. I said, wow, that's really nice. Can you send me the solution? Nobody got it. And those who wants to hear the nice parts, I'll tell it after the recording. But the end result is that this is still an open question. I submitted, it was accepted to ITA 2014, went to a conference talking about riddles like that. And if you want, one of the reasons for this kind of seminar is to give you ideas for future research. Try this one. I have, maybe I can go back to the one I skipped. I have few.
Do you know the errors function of that in general, like topic?
There are bounds, lower and upper bounds. Some of them are trivial. For example, if you want to convey 5 bits, you can always do it in 33 houses. One is the input, and Bob actually tells Alice. So that's a very simple bound, and you can't do it. Yes, this function, what actually did is it got a string and outputs the index of this string in the list of sorted the strings that have the same letters, all the anagrams of this string. The way it did it is go over all to 256 to the k is the length of the string possibilities, first checking that the histogram of the different letters equals to the input, meaning that it's an anagram, and if so, increment the counter. And when the counter, when you get the original string, you print the counter, and it's a exponentially long program running big numbers, etc. That's the one here. I have the reason I'm here is because I gave a talk at the Technion about this talk. Wrong mathematical proof for possibly correct claims, and I use the same idea as a riddle. It's not the room number. So first of all, you can, if you remember the computer, the assembly, it started with B8. B8 is move immediate to AX. And 2024, the little Indian, it's the year. So that's the year of the talk. And I gave the talk, it's the B8th day of the year. So that's the riddle for them. And I talked there about a lot of things. I put it here as a filler if you don't have questions, and I can give you a very short run through this talk. Wrong proofs. There are a lot of ways to prove the things in the wrong way. One of them is hand waving. So, for example, a friend of mine sent me a proof for the Goldbach conjecture. The weak conjecture, it's a theorem proved 10 years ago, is that every odd number can be represented as a sum of 3 primes, large enough odd number. And the hard, the conjecture, the open one, is that every even can be represented as a sum of 2 primes. And what he said is, it's very simple. Give me an even number, any number you want. Now I'll add a large prime number to it. It's odd. Since it's odd, from the theorem, you can divide it to 3. Now I'll take the prime I added back, and give you the two primes that were left. So this is a very nice, very enjoy. In some audiences, not all of the people laugh from this. Social engineering, and again, if you want, you can see this nice movie. The father and daughter are traveling in the US and cheating people in all nice ways. Just hand waving, social engineering. That's another aspect, the cybersecurity aspect of hand waving. And I have another example from my work. I have to do some part that should compute the maximum of numbers, and I did it the way that it was done was the optimal way, and then I found another way which was better than the optimal way, because it's not always optimal. Induction. If you drop this domino, you'll drop all the dominoes. So a mathematical proof, all finite set of horses, all horses have the same color, a very famous one. A Tetris game. It's a story about a real story about somebody traveling in a plane, playing Tetris, hacking the game, and crashing the entertainment system. He didn't crash the plane because they had a very reasonable separation between the entertainment and the flying system, but how he did it was actually another example of failed induction. It's a nice story. Spectral meltdown, you prove that things are okay, you can't access memory you don't have, and then after you prove you add some optimization in the caching, etc., and you don't go back to your proof and you break the the induction says that I'm born in a good state, and whatever I'll do, I'll stay in a good state. That's why I'll always be in a good state. But if you somehow like in the horses, failed some step or do things in the wrong way, then you can crash the system. And that's why software engineer, salesperson, and mathematician, computer science go to the deserts, and the car has a flat tire. The salesperson says, "Oh, you just take the car on our backs, walk 50 miles. We'll have to the nearest town, we'll sell the defective car, buy a new one, a better one, cheaper. Trust me, I'm a perfect salesman. I'll do whatever is needed." And then the engineer says, "It's very hot, walk 50 miles with a car on our back. We have a jack, spare tire, let's replace the tire and drive to the city, sell, buy whatever you want." And then the computer science person said, "You engineer are always resulting to hardware solutions. Just close the car, restart it, it will work." And why does it work so many times? Because you go back to the induction, you made some mistake, you get into a wrong place, you shouldn't be there, and usually a restart will get you back. So if you understand why wrong proofs work, and why not, you can use it. Testing, Ilya is here, he can tell you a lot about testing. So for example, in 1978, the four-color conjecture was proven, and 11 years later, it was shown to be a wrong proof. Some small testing case was missing. So that's an example. The color code is blue is mathematics, red is cyber, and green is chips. I like to show it in a course that I'm teaching, how to win Super Mario. The way the crux of the solution is Super Mario boards Yoshi, this dinosaur, and tell him to eat this mushroom. And he opens his mouth and sticks his tongue out. Before he does that, he looks ahead of him to see what's going to be eaten. And if it's unedible, then he doesn't open the mouth. You can't do it. But if it is, then when he gets the sprite into his mouth, he runs a case statement and do whatever happens in the different cases. So the trick is tell him to eat the mushroom, disembark, take the mushroom, put an edible thing in its place, and then Yoshi first tests to see it's edible, so he tries to eat it. While by the time he eats it, it's unedible, and he runs out of the case to no man land, some random place in the memory which is not mapped to anything, and of course crashes. And here comes the nice part. So first of all, this is a bug. You could test it if you could find it if you test enough. But the nice thing here is how to use this bug to win. So before doing that, he spends a minute putting things in different places, and every thing in the game has a place, and there is a memory where X, Y are these things are. And if you are looking to the left and you are not streaming and all kinds of very carefully, you can actually run the XY position of the things as code. So after crashing, you make it go to the place in memory where you carefully wrote the program. And what the program there does is go to the end game. It's not that simple because you don't have enough space, so you have to cheat a little more, but that's the idea. 11 minutes video, a very nice one, Super Mario. And the Intel floating point divide, that's the same here, don't access in the memory, etc. Okay. The Technion, I wasn't rushing through that. Each line here is a different slide, but as I told Rani, I don't like giving the same talk twice, so I can. How much time do you have?
Till 12:10, including questions.
Okay, so any questions? Do you want to? I have another message, this one. If you want more events, I have two. One of them is from Men to Tetris. We are inviting Shimon Shokin to give a talk it's next Silicon, and it's this week, Wednesday. And on December, there is a conference that I'm organizing, HPC plus AI, high performance computing, where you'll hear what we have, what is our solution doing, and other startups. If you need a 25.6 terabit per second communication, if you want to compute things faster than the B200, then come to hear about the solutions. Oh, and that's the first part of the conference. And the second part is the part that people will tell about the needs for HPC. So Oded Schwartz from Hebrew University will tell about fast matrix multiplication, autonomous driving, all kinds of nice things. So, yes.
I don't think so.
Oh, yeah. So that's a great demonstration of why you should test things. I thought I tested it, but you forgot. Oh, yeah. I'll send you the link. Again, thank you for spoken. Any other questions, or you want to hear more about any of these, or ask questions? Show you.
Any other question? Thank you.